Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to introduce Vlad again. Vlad was here for 2 summers for internships. What, 2-3 years back now? No, 2 years back last time.
4 years back. Yeah.
3-4 years back. Already forgotten that. And yeah, we've done some great work. He was a contributor to the full duplex things, to the recent NSDI paper, to a lot of stuff. He worked with MSR India as well recently as an intern. And so today he's going to talk about the recent Mobicom paper. And I asked him to keep the wireless bits simple so that you can all follow. And but if
we can follow the complicated stuff as well.
Okay, but if you're interested, you can. I said you last question, so I count on you now asking about MIMO and all this. Yeah, and then of course interrupt, I guess.
Yeah.
So to you.
Oh, both of them, or
No.
just this one? All right. Thank you very much for being here today. I would like to share with you some recent work that we have done at USC on distributed multi-user MIMO. As you know, multi-user MIMO is rapidly advancing towards the market. It's almost there as 802.11ac, and there's considerable interest in realizing its complete potential. And while doing that, investigating what's achievable from a technical point of view. Now, 802.11ac is the baby version of multi-user MIMO, and what I'll talk about is distributed multi-user MIMO. So distributed MIMO from multiple access points. First of all, a few words about our technical platform. We do experiments using software radio, which are, in their more sophisticated form, small systems on chip built in FPGAs, capable of performing real-time operations. They have one or more RF front ends, coupled with ADCs and DACs for sending waveforms. So think of them as sound cards for wireless signals that operate at 2.4 gigahertz, for example, frequency. They have a CPU, RAM, and most importantly, they have a clocking architecture that's designed to support MIMO operation. So in MIMO, it's always important how your phases, the phases of your signals are aligned to each other. And the first step in doing that is making sure that the clocking of your electronics is designed to maintain phase alignment, at least on a single box, on a single software radio. The software radio that we use is the Warp platform, created at Rice University. It features RF front ends, a Vertex FPGA, and a dedicated clock board for driving the electronic circuitry. It's a very common platform. I think tons of groups are using it by now. In our testbed, we linked 8 of these radios to a server machine. We run on the server MATLAB and the Xilinx tools for developing the signal processing circuits that are hosted on the FPGA of the Warp board. To the same Warp FPGA, we ported NetBSD, since having a solid software stack is a prerequisite in developing any viable wireless design. So for example, here's a problem that we had. We want to encode our signals on the server in MATLAB and send them through in real time to the radios. But that's a lot of data. So for a 20 megahertz channel at 16-bit INQ channels, we have to send something like 640 Mbps. And it so happens that the FPGA processor cannot handle that. So we needed to develop a zero-copy approach just to push data from the Ethernet of the FPGA to the RF front end. So that's why we started tuning the Warp. How do you develop for Warp? Well, first you create a circuit design. This is Simulink, which is capable of taking these circuits as blocks and translating them all the way down to FPGA, to bitstream logic. Then you take that circuit design and you integrate it in a small system on chip that you develop on the same FPGA as a device. So this looks to the FPGA much like a network card, let's say. Even the way you transfer data is the same with DMA rings and buffers and so on, and buffs. And then you go to NetBSD and you program kernel drivers for all the devices, for all these operations. And then I said that we use MATLAB for the signal processing. So you implement all your precoding schemes or your algorithms as MATLAB code. And these waveforms you can send to the radio to see how they look like over the channel. Now you cannot do everything in MATLAB, especially the synchronization aspects that I'm going to talk about. And I'm going to make it very clear what's the division between the precoding that is done in MATLAB and final steps that have to be done in the FPGA in real time. All right. So much about software radio. Let's talk about the actual research. So what's the reason to investigate MIMO? Where are the gains? Well, there seems to be a bit of spectrum shortage, and distributed MIMO seems to be the best available answer to this shortage since it provides spatial multiplexing as a way of achieving a rate gain. And as you know, spectrum is very scarce. Cellular companies spend billions for bandwidth. So spectrum reuse is definitely something to try. On the Wi-Fi front, well, spectrum is not so scarce, but then if you walk into a Starbucks and you have 20 users sharing the same Wi-Fi network, you're going to see that the rates are nowhere comparable to your own home. So the setting for our research is enterprise Wi-Fi, where you have a whole bunch of access points connected to a single server, serving multiple clients. And actually, they communicate with each other. They share channel state information. They share their precoded data. So the server is basically the brain of this system. So if in a normal access point, you will have multiple antennas, and we have the access point doing the whole precoding and the whole communication with every client. Here it's the server that's the brain of the system, and the access points, they just have to fulfill the antenna role. So I will present three things. I will introduce multiuser MIMO and the precoding schemes that we use. I will talk about our contribution, which is distributed MIMO and the synchronization of such a system. And then I will present the experimental results. So let's talk a bit about multiuser MIMO. There's quite a bit of demand for more wireless bandwidth in order to keep up with the transfer rates on the wired internet over the last hop, which is more often than not nowadays wireless. And well, to be precise, wireless bandwidth is not the thing to ask for. What you want are higher wireless transfer rates. But, as Shannon says, transfer rates and bandwidth are closely related. And if you want to increase your transfer rate, the easiest way to do it is to try to increase your bandwidth, because then the power consumption increases linearly. While if you try to increase your transfer rate by just increasing your power, you're working after the log factor, and you have to increase your power exponentially. So any form of multiplexing that seems to give you more bandwidth is more advantageous than trying to solve the problem by just increasing power. So in a wired system, you increase your bandwidth very simply. You just run another line, and you double your bandwidth all of a sudden. In a wireless system, on the other hand, the different connections interfere with each other. So you cannot just simply create more point-to-point connections. What you have to do on there is to do joint precoding between all your antennas to every user and try to limit the amount of interference that is leaked from one user channel to another. And we know that what's the optimal way to do that. It's called dirty paper coding. And it also provides you with the achievable rate region. Now, dirty paper coding is a theoretical concept. It's not been implemented yet because it's as implementable as Shannon's scheme, for example. But there are some pretty good approximations, which we tried. So let's talk about the precoding schemes. So assume that I would have a system with 4 users and 4 access points. And I have the channel matrix, the one in the middle in gray, and I would just simply send my data for each user to the channel. Basically, what I would get on the other hand would be something completely mangled, because every user would hear everyone else's symbol with different coefficients. So what would I like to have instead? What's the equivalent of the picture before, with every user having its own channel? I would like to diagonalize this channel matrix to get the same symbol for every user at every user on the left side, on the receive vector. And the way to do this is just to multiply my user symbols with the inverse of the channel matrix, or the Moore-Penrose pseudo-inverse, actually, to be precise, and send that over the channel. So this is the actual pre-coded data. And this is called zero forcing. And this is the most common MIMO scheme used nowadays, the most common MIMO pre-coding scheme. The other scheme that we have tried is Tomlinson-Hiroshima precoding. I'm not going to talk about it here. I will just say that it's a bit more advanced in linear algebra. It's a bit harder to ingest over just a few seconds. So if you know it, that's good. But if not, I'm not going to try to teach it to you right now. And that scheme has the advantage that it's a very, very efficient approximation of the dirty paper coding. So we know how close it is to the optimal. We know that you only lose a few fractions of a bit for every user channel with that scheme. And these schemes are very good when you have the channel state information, but actually collecting the channel state information on the transmitter side, it's one of the biggest overheads of deploying a MIMO system. And now if we are talking about MIMO systems with lots of antennas, with let's say 20 antennas for all the access points in this room, and 20 users, that gets to increase quite fast. So then what we can do, there's been considerable interest in schemes that can get a multiplexing gain, that can send more data without using channel state information. One of these schemes is blind interference alignment from Jafar, from UC Irvine, in which you can send your symbols in a certain pattern. You actually use multiple antenna modes on the receiver. You get different perspectives of the symbols you send. And then you do linear algebra on the received symbols. And you're able to recover all your original data. Now the downside is that the gain that you get is not the same as before. So before you were getting a linear gain in the number of antennas. In a 4x4 system or in a 2x2 system you get a gain of 2. In a 4x4 system you get a gain of 4. Here the gain is less. So for example, in a 2x2 system, the gain is only 4/3. So much about precoding. Let's talk about distributed MIMO. So in normal MIMO, you have all your antennas hosted on a single access point. And because the access point is using the same clock to run every RF front end and every antenna, the phases in your system are synchronized. Now, I'm going to make the case that you need the phases to be synchronized also across access points when you're using multiple access points together. And I'm going to tell you how we achieve that in our own system. So what's our synchronization method? So as I said, the natural setting is an enterprise Wi-Fi network with all the access points distributed and with a single server controlling them. We assume every parameter of the network to be identical to those used in 802.11 AC, which is the upcoming 802.11 standard. Now 802.11 AC works with one access point, while here we have to coordinate all of them. What are the challenges in realizing this? Well, you have to maintain the phase synchronization between the different APs, and you have to gather the channel state information and transmit before the channel coherence time ends. For synchronization, the hardest part is aligning the phases, where you need an accuracy in the picoseconds. And the second hardest part is estimating the transmitter's carrier frequency offsets, which basically make the phases of the transmitters drift away from each other. So even you have an estimate at a certain point, that estimate is only accurate for a few OFDM symbols. Afterwards, it dies. So I mentioned OFDM. OFDM is the modulation of choice for wireless nowadays. It replaces a single carrier with multiple subcarriers, so it divides the bands into multiple portions. And then it divides the time into slots. So you have OFDM symbols, one after the other, and it prepends to the beginning of each slot a copy of the end of the slot as a cyclic prefix. Now, this cyclic prefix has two purposes. It's intended to combat the effect of multipath, so of different paths in your system that give you a longer response time of the channel. So this would create inter-symbol interference. And the other purpose is to let you basically play a bit with a time interval that you want to decode. So what you have is that the IFFT produces this OFDM symbol with a cyclic prefix, and then you have to find an interval of the original length to decode through an FFT. Now, when you decode the superposition of two OFDM symbols from two different transmitters, you have again to find the common interval of this length, and this puts a requirement on the symbols themselves. They have to be aligned within the cyclic prefix, otherwise this interval doesn't exist. So this is the first requirement in a distributed OFDM system, the symbol alignment. But then if you want to do MIMO, you have to have also phase alignment. Now the symbol alignment, the tolerance there is on the order of the cyclic prefix, which is a few hundreds of nanoseconds. For the phase alignment, if you do the math with a carrier frequency of 2.4 gigahertz, if you only want to be off by 1 or 2 degrees, the tolerance is in the picoseconds. And if you're talking about phase, what are the factors that come into the phase of the different transmitters? Well, first of all, you have a random phase induced by the electronics on each transmitter. Then you have a timing offset which rotates the phase of each carrier in a different manner. And then you have the carrier frequency offset, which basically makes the phases drift at different slopes from each other. And you have to take each of these three effects into account when you're synchronizing two systems. So you have to basically determine initially the random phase, and then for each packet determine the timing offset and the carrier frequency offset. Otherwise, you will not be able to compensate them. Now, each of these random phases that I was talking about from each transmitter and receiver, so for example, the ones from the transmitter, multiply each signal going through. The receivers do the same. So on a connection from a specific transmitter to a specific receiver, you have two random phases, the random phase of the transmitter and the random phase of the receiver. So going back to MIMO, what this means is that in your system, instead of having the standard channel matrix from antenna to antenna, you now have these three matrices, the standard channel matrix in the middle, and then two diagonal matrices, one on the left and one on the right, which are the random phases of the receivers and of the transmitters. Now, the matrix on the left is not a problem. That's in every OFDM receiver, and we know how to deal with it. But look at what the matrix on the right does. For every symbol that is received, so for every line of the channel matrix, it multiplies the symbol from each antenna with a different random phase. So in MIMO, there's the concept of beamforming, of aligning the phases from the different antennas to get a coherence gain. And what this means is that you cannot do the beamforming anymore. If you cannot do the beamforming, the other thing that you cannot do is the zero forcing. You cannot do the matrix inverse. So then, the question arises, can we live with that or can we not live with that? So what should the effective channel matrix be? Should it be just the matrix from antenna to antenna, and we should somehow take care of the matrix on the right? Or should we make that part of the channel matrix, say that the channel matrix actually has a very small coherence time, depending also on the electronics of the channel, and use a precoding scheme that estimates this matrix in every transmission time slot and then precodes using it. And there are precoding schemes and systems that use that. For example, the recently published Argo scheme from RISE uses uplink channel state estimators. So basically, they send from the receivers to the transmitters, and they collect the image of the two matrices together, and then they precode using this combined matrix. But the problem is the coherence time becomes very short, and if you want to use a centralized scheme which takes time to collect good channel state information and then takes time to process it and encode the data for the users, you don't have that option, and you have to stick with option 1. And what you have to do is, for the right matrix, lock all your phases, so lock all the phases of the transmitters, so that they still seem to act as a single co-hosted MIMO system. So how do we do that? I already said what we are estimating, the timing offset that gives one phase rotation, and the CFO that gives the different phase drifts. And how do we estimate it? We select one of the access points as a master, transmitting pilot signals to the other access points, which are secondaries. And these access points, after obtaining these estimates, they act basically as digital PLLs. They synthesize their signals to be in sync with the master signal. So what we have are phase synchronous signals from all the transmitters, from all the APs, going to the user. And this way the beamforming is preserved. Questions so far on the synchronization scheme? Okay. So then I'll go to the results sections and basically say.
So sorry, how do you get the picosecond? It's really like.
Good question. Basically, we are saying the following. This is very, very similar to an OFDM receiver that works in real time. An OFDM receiver has to do all of this, has to lock onto the CFO of the transmitter, has to lock onto the phase, has to maintain the lock. And this is all signal processing done in the baseband. So we never actually clock the receiver in the same way as the transmitter. Now, I have the carrier clock from the passband of the master to the baseband of the secondary as a fixed phase, right? Now, if I create a signal that's synchronous with that at the baseband, and I use the same carrier clock to bring it back up to the passband, basically the synchronization is maintained also at the passband. So if I look at it symbol to symbol at the passband, the secondary is doing exactly the same thing that the master is doing.
Does this rely on these access points being fixed, not being moving, being very stable configuration?
Yes, the access points have to be fixed.
And does the wireless environment again have to be relatively fixed or not?
Between the access points. So not between the access points and the clients. We have no requirement there further than...
Between the master, I think between the separate access points. So.
Yes, between the master and the secondaries it has to be fixed. So I think in a Wi-Fi setting that wouldn't be a problem. The access points would be somewhere around. If you...
Why would that? I mean, it seems that the more difficult thing is to estimate the clock drift, which doesn't depend on the environment. The environment is like the usual Wi-Fi stuff you estimate after a packet or so.
Yeah, so this is a rough requirement. If you go into the estimation part, a lot of these factors cancel out. So basically, you would need the environment to be fixed from packet to packet, which is not a very, very hard constraint. It doesn't have to be fixed over very long times. So we actually done an experiment with software radio. We created a 4x4 testbed with 4 access points and 4 receivers. And our baseline is the TDMA case, because that's what's happening in networks today. And we basically took the best connection in our testbed, measured its achievable rate, and used that as a comparison point to doing the joint precoding, so to the sum rate when precoding from all the access points and sending to all the clients at the same time. And here are the first results. So zero forcing beamforming. This is a 2x2 case. Basically, you see that we created two channels, two clean channels, one for every user. And this is the result of good phase accuracy. So this is the CDF for our phase accuracy, and with 90%, 95% confidence, we are with a phasor. We have a phasor less than 5 degrees. And this translates into the following curve. That means that the leakage from each one of these user channels to the other user channel is somewhere between -20 and -30 dB. So each user leaves the other users with 20 to 30 dBs of SINR. And this is a pretty good wireless channel. The other scheme, which I have not presented, Tomlinson-Harashima precoding, has very similar results. So these are the rates, and this is the rate gain for that scheme at different base SNRs for the system. And we got in a 2x2 scenario an 85% rate increase. Now the theoretical gain is of 2, so we got 85% of the theoretical gain. In a 4x4 system, we get 60 to 20 dBs on each channel for each user, which means that the rate increase is 165%. So the gain is 2.60 something, 2.65. But the theoretical gain is 4, because now you have 4 degrees of freedom. So we are only getting 55% of the theoretical gain. And where does this mismatch come from? It comes from the phase alignment not being good enough so that the leakage, when you increase the number of users, doesn't degrade your channel more significantly. So this is the place where we have to improve our system now, get an even tighter phase alignment. For blind interference alignment, we were not expecting the same gains, and we don't get them. So the green line is the blind interference alignment. We get on average a 22% rate increase. Now I said at blind interference alignment that the multiplexing gain is 4/3. So the rate increase should be 33%. So why are we getting only 2/3 of that? Well, blind interference alignment does quite a bit of linear algebra. And that means that it mixes symbols together in order to get the user symbols. And that leads to something that's called noise enhancement. So basically adding together the noise from every partial symbol. So that's the reason behind this lower rate. Now, to get a theoretical base point, we did some MAC-layer experiments. We compared scheduling strategies through simulation for a scenario in which we had 4 AP, 8 users, and we used back pressure to schedule them. And the schemes that were tried were zero forcing with a greedy allocation of the users, Tomlinson-Harashima, and blind interference alignment, and of course TDMA. And this is what we expect. So in a 4x4, we expect that zero forcing and Tomlinson-Harashima are very close to the theoretical limit from dirty paper coding, so almost a factor of 4, while BIA is, blind interference alignment is significantly lower. So the gains are a lot less. So you get linear gains with schemes that know the channel state information, and you get a lot less gain with schemes that do not know the channel state information. So the discussion about the overhead of finding the channel state information should take this into account.
Is that still, I mean, are you assuming still that there's still a kind of almost a very stable wireless environment? There's a lot of secondary fading or deflection effects. To me, you can always, ideally, you'd always be able to estimate the channel matrix. Then is that what the simulations assume, even in the unknown state?
No. So the blind interference alignment is geared more towards cellular, where you would like to get to get a multiplexing gain if you could, but channel state information collection is very expensive, and the coherence times are very small. For the others, it should be perfectly achievable to get the channel state information. That's it.
Thank you said some part was done in MATLAB, the other part you had to do the FPGA.
Exactly. So the part that was done in MATLAB was all the linear algebra that takes the channel state information into account. So we take the channel matrix, we take it into MATLAB, we do the linear algebra, we create the waveforms. The part that you have to do in FPGA is the final phase rotation, compensating for the right matrix, because that's something you do based on incoming data, and you want the response time of your system to be very small. So in our system, it's something like 5 OFDM symbols. That's basically the circuit delay through the FPGA. And for that, you couldn't wait. I don't think it's feasible to wait until you send the data back to the PC and respond, because these phases, they drift from each other. The electronics won't wait.
But the MATLAB recording is done on that data that was fed from the real system.
Yes, yes, yes. So we get actual channel state information.
So what the limits happen as you scale up the number of the size of the system? And what happens to the complexity? I mean, obviously you've got calculations you need to do to which get more complex with scale as the sort of at least the square. Is there any problem as you scale up the number of?
Yes, there are a number of problems. So the theory predicts that the rate should increase linearly. So you just allocate linearly more power and you get linearly more rate.
Yeah.
The problem is the leakage, because if your synchronization is not tight, you have more and more leakage to the users that are not supposed to get those signals. And then your noise floor increases. So the better you get your synchronization working, the more scalable your system becomes. There are other problems like the overhead of channel state information, the scheduling of the users, so that you don't, I was talking with Bozidar, you need to do some kind of power allocation so that you don't transmit to a user that's very close than to a user that's very far, because then you're basically leaking a lot more. But yes, in principle, the accuracy of your synchronization is the main limiting factor.
And how much do you think you can scale? I mean, with the current system?
Well, if I would, increase the accuracy by a factor of 4, we could already talk about something like 16 antennas on the access points and 16 users. Now, in communication theory, you talk about bits per second per hertz for spectral reuse when you compare systems, when you say how good a communication scheme is compared to the other. Now, with 16 simultaneous streams at normal QAM constellations, 4 bits per second per hertz or 6 bits per second per hertz, the sum rate would be so high, it would be much higher than anything that's currently deployed. I think LTE, which is the standard nowadays, it's as optimized as it can be, gets 16 bits per second per hertz. Now you will get, I don't know, 40, 50, maybe more. So I know the RISE guys, they tried in a similar system. So they don't do distributed MIMO. They do MIMO from a single rack of warp radios, which are all clocked together. So they don't have the distributed aspect working for them, because when you do distributed MIMO, the channel matrix looks better. You are closer to the user, so you get less interference from the others. But they tried this from a single rack with 16 radios clocked together, transmitting to multiple users. And when they tried zero forcing, they got 96 bits per second per hertz, which is a huge number.
Vlad is around for a while after